I think I should start. And my name is Katsuaki Tanabe from Kyoto University. Oh, thank you. Thank you, Jim. I'm gonna tell you how we can improve or enhance the CF effect by utilizing surface plasmon photons and just a theoretical work for this time. Alright, so as I took a little survey for the injected power for the earlier experimental works for CF field, and my conclusion for that is that the injected power is on the order of 1 watt per square centimeter, and so this is the basic value for the injected power for both of the liquid phase and gas phase experiments so far. Probably you can raise your hand if you apply much more, and we can apply much more power by utilizing lasers or such optical technique because even for the conventional or well-established semiconductor lasers, we have a couple of magnitude higher intensity because the laser light is very focused locally. And by using high power lasers such as YAG lasers, we can apply even further. And probably some of you have already tried in your experiment by injecting laser and to enhance the reproducibility of the fusion reaction. And this time I calculated the field enhancement factor around metal nanoparticles in the electromagnetic field or incident optical light. The field enhancement factor is defined as the intensity ratio in between the field around an object based on those under no existence of such object or metal nanoparticles. So we can know how much energy is enhanced by the existence of metallic nanoparticles or such substance. And this is the calculation scheme. It's a very basic classical electromagnetic theory, and don't worry, I do not use anything exotic. This is just Maxwell's equation, and I calculated the electromagnetic field for the optical light which are passing through a metallic nanoparticle. And I get finally this equation for just calculating the field under the existence of a substance and without such object. And then just by simply taking a ratio, we can know how much energy or optical field is enhanced by the existence of the nanoparticle. And the key of this enhancement is the surface plasmon again, and which is the strong correlation in between the incident field and the metallic free electrons by the oscillatory movement of the free electrons inside the metallic substance. And this phenomenon is particularly enhanced for nanoscale metallic particles whose dimension is similar to the incident wavelengths. And this is a calculation result, and we can see for variety of metal elements, we can have more than 10 times enhancement of the field. So field means which can be applied for the liquid phase experiment because they apply electrochemical method and the field is enhanced around the metallic nanoparticles. And for both of the liquid phase and gas phase experiments, we can expect by utilizing metallic nanoparticles, we can enhance or localize the energy of the electromagnetic field around the metal. So probably particularly for the condensed, the atoms close to the surface of the metal, such as platinum, we can see that effect, and probably can harvest the effect to enhance the CF reaction. And when we see for the conventional metal elements such as platinum, nickel, titanium, we also see the enhancement effect around 10 times for both of gas and liquid phase systems. So probably unconsciously we had already had this effect in the earlier experiments, and so probably this effect can be incorporated for the future analysis of CF experiments. And so far I have talked about simple spherical metallic nanoparticles, but let me switch my gear a little bit and gonna talk about metal nanoshells. Nanoshells consists of a metallic shell with and dielectric core, so like core shell type nanoparticles. And particularly for this system of material, we can have even higher field enhancement effect thanks to the hybridization of the intrinsic spherical plasma mode and the cavity mode. And for the like molecular interaction, we can have bonded state for lower energy, and this mode can highly interact with the incident electromagnetic field or light. And again, I calculated the field enhancement factor for such a core shell nanoparticle structure. And this is a calculation result, and we see this is an example for nanoshells with silver shell and silicon dioxide core, and we see about 1,000 times field enhancement factor, which is namely the energy enhancement effect. So the applied, for example, electromagnetic field in the liquid phase electrochemical experiment, as well as like laser fusion type gas phase experiment, we see such we can have by utilizing metallic core shell structure, we can have such energy enhancement effect. So maybe effective for the higher reproducibility of the fusion experiment, or higher gain. And because my model based on the classical Maxwell equation is very simple and easily applied to any kind of metallic shell and dielectric core material combinations. As I tested just to see what kind of combination of the material is the best, and I see the core material should be better for having lower refractive index, such as oxide or like Teflon, or even, thank you. If we could have a hollow type, so like the air core, that would be the best. And the shell materials may be good by using novel metals such as silver, gold, and platinum could be a little bit lower, but still fine. And so the resonant wavelengths, as we saw the previous result, the resonant wavelengths can be tuned simply by the ratio of the core and shell thickness or diameter. So for example, if you use laser to activate the reaction, for the wavelengths of the laser, we can change the structure and simply tune the resonant wavelengths to have higher enhancement effect by changing the structure. So which is very useful and flexible in experiments. And by using such technique, we can focus the laser or electromagnetic field energy locally onto or close to the surface of the platinum for conventional CF experiments. And then this technique can be applied both for gas and liquid phase systems, even without any light injection, because by using the electrodes for the area conventional experimental system, the electromagnetic field is simply equivalent to the light, because that's all electromagnetic field, of course. And then so I hope, and actually I'm currently making experimental setup to experimentally verify this effect, how the core shell metallic nanostructure is useful for enhancement of our CF reaction rate. And this scheme is also applicable for laser fusion technology, and by simply embedding metallic nanoparticles or nanoshells into the conventional deuterated polystyrene field target, which is commonly used for laser fusion field, in my calculation, I got very high enhancement of the energy. So probably to trigger the initial stage of the fusion reaction, this technique can be applied. And I also making some mass transported heat generation model to macroscopically investigate or analyze the experimental result, and which will be eventually connected with the electromagnetic field model to thoroughly or exclusively understand what's going on in the CF experiments. And so I hope I can show you some all-in-one type of model, and as well as some experimental results in the next conference. And this is a summary of my talk, and thank you very much for your attention.
Now, question and comments, please.
Have you done a model